Your most classified enterprise data is exposed to catastrophic theft every single time your cloud AI models process an unencrypted request, creating an unacceptable breach vector for modern digital operations. Traditional encryption protocols effectively safeguard your information while it rests inside secure databases or travels across protected networks, but they completely fail the moment computational processing actually begins. To execute standard cloud AI inference, public networks require your teams to completely decrypt raw corporate data packets at the remote third-party endpoint before generating any predictive neural outputs. This critical decryption window represents a massive corporate friction point, exposing sensitive intellectual property, operational logs, and proprietary financial metrics to sophisticated external actors and malicious multi-tenant cloud sniffing. When data sits exposed in server memory, it violates the core principles of modern zero-trust architecture, leaving your enterprise highly vulnerable to sophisticated memory scraping and advanced hypervisor side-channel attacks. Regulatory bodies worldwide are dramatically intensifying their data governance standards, meaning that any temporary exposure of private consumer records during remote cloud processing could trigger devastating compliance penalties. Fierce market competition demands that organizations utilize public cloud scalability to drive their complex machine learning models, yet security mandates continuously restrict the raw data pipelines available for public inference. Security leaders cannot simply block AI integration because corporate productivity depends on advanced automation, creating a paradoxical gridlock between operational velocity and strict information assurance paradigms across the enterprise. Legacy perimeter security systems fail entirely here because they only protect information during transit, leaving the core computing workspace completely blind to malicious inside actors operating within the host infrastructure. This operational vulnerability is further compounded when utilizing shared public multi-tenant environments, where virtual machines from competing global corporations reside on the exact same underlying physical server hardware clusters. As organizations ingest massive data streams to fine-tune their competitive market position, the absolute risk of accidental leakages at the point of computation expands exponentially, threatening long-term enterprise viability. The overarching security dilemma is now completely clear, forcing architectural teams to find a definitive mechanism to run high-performance neural networks without ever exposing raw plaintext assets to external servers. The architectural resolution to this critical corporate liability lies within advanced homomorphic mathematics, specifically realized through the implementation of emerging enterprise fully homomorphic encryption pipelines, commonly abbreviated as FHE technology. Fully homomorphic encryption represents a revolutionary paradigm shift in data security, enabling computer systems to execute complex mathematical operations directly on ciphertext structures without ever performing a single decryption phase. By utilizing intricate algebraic ring structures, FHE mathematically guarantees that the result of an encrypted computation, when finally decrypted by the data owner, perfectly matches the plaintext processing output. This means an enterprise can securely encrypt their highly confidential data packets locally using their own private keys before uploading the protected ciphertext to a third-party cloud infrastructure platform. The cloud host receives only mathematically obscured noise, possessing absolutely zero capability to view, read, or manipulate the underlying sensitive corporate records, intellectual properties, or transactional user identities. When the cloud-hosted artificial intelligence engine initiates its inference pipeline, it treats the incoming ciphertext as a series of complex mathematical inputs, evaluating the neural layers homomorphically. The artificial intelligence model applies its foundational weights and activation functions directly to the encrypted mathematical structures, modifying the values while they remain completely sealed against external visibility. Every matrix multiplication, tensor addition, and neural layers operation within the transformer architecture is converted into a structured sequence of homomorphic additions and multiplications on the underlying ciphertext elements. Because deep learning models are essentially massive, sophisticated mathematical equations comprised of sequential linear algebra operations, they are uniquely and perfectly suited for translation into homomorphic execution spaces. The cloud infrastructure executes this entire rigorous inferencing workload without ever converting the processed files back into human-readable plaintext, maintaining a continuous posture of absolute mathematical data isolation. Once the cloud model completes its advanced homomorphic inference cycle, it outputs an encrypted result token, which is then transmitted straight back to the originating secure enterprise perimeter. Your local on-premise infrastructure, holding the exclusive decryption keys, decrypts this return token to reveal the final AI prediction, completely bypassing any external data exposure risks during processing. This complete mathematical paradigm successfully neutralizes prominent attack vectors detailed across global security standards, ensuring that compromised hosts cannot intercept the sensitive assets actively moving through their systems. By integrating these robust, homomorphic mathematical frameworks, modern companies can confidently leverage the immense computational scale of external cloud hyperscalers without sacrificing their strict digital sovereignty mandates. The resulting deployment architecture effectively decouples the underlying computational work from data visibility, establishing an impenetrable cryptographic perimeter that remains fully active even within highly untrusted host spaces. This secure transformation redefines the boundaries of enterprise cloud computing, providing a mathematically validated solution that completely resolves the fundamental trade-off between technical innovation and robust information security. The direct macroeconomic impact of deploying fully homomorphic encryption is profoundly transformative, fundamentally shielding large organizations from the catastrophic financial fallout associated with corporate data breaches. By eliminating third-party data interception threats during live artificial intelligence processing, businesses can completely insulate themselves from severe regulatory compliance fines across multiple highly strict jurisdictions. Global data protection laws impose devastating financial penalties on companies that suffer breaches, making proactive cryptographic security an absolute fiscal necessity for maintaining stable corporate balance sheets. Beyond avoiding legal penalties, adopting advanced FHE systems directly enhances long-term corporate valuation by firmly protecting priceless intellectual property assets from industrial espionage and unauthorized competitive replication. Enterprises operating within highly sensitive sectors like defense, healthcare, and global finance can now accelerate their digital transformations, unlocking massive hidden value previously restricted by security compliance overheads. This security breakthrough triggers a profound reallocation of corporate capital, shifting defensive IT expenditures away from post-breach remediation towards proactive, highly strategic cryptographic infrastructure development projects. As FHE reduces the total financial risk of public cloud deployments, insurance conglomerates are restructuring corporate cybersecurity policies, offering substantially lower premiums to organizations utilizing validated homomorphic pipelines. Simultaneously, this technological evolution is driving massive structural disruptions across the global technology labor market, shifting traditional engineering roles toward highly specialized mathematical and cryptographic competencies. Standard information technology operations staff are transitioning into highly technical FHE infrastructure engineers, a critical new role tasked with managing complex encrypted pipelines across distributed cloud clusters. This structural labor shift requires traditional system administrators to master advanced concepts in lattice-based cryptography, polynomial mathematics, and specialized hardware acceleration topologies to remain viable in the industry. Educational institutions and corporate training programs are rapidly realigning their core curricula, rushing to fill the severe global shortage of engineers capable of implementing these complex mathematical frameworks. Organizations that proactively invest in upskilling their workforce will secure a significant competitive advantage, cultivating an elite internal tier of architects who can safely deploy advanced artificial intelligence. Conversely, enterprises that fail to adapt their technical staffing models face acute operational bottlenecks as their traditional security teams struggle to manage the computational overhead of homomorphic systems. The demand for these specialized skills is driving massive compensation increases for qualified professionals, rewriting the macroeconomic landscape of corporate IT talent acquisition budgets across the globe. This comprehensive transformation of human capital ensures that the future of enterprise technology will be guided by professionals who view information security through a lens of absolute mathematical certainty. Ultimately, the microeconomic benefits of data protection and the macroeconomic benefits of labor optimization converge, establishing FHE as the foundational pillar of the next-generation digital marketplace. Executing a successful enterprise deployment of fully homomorphic encryption requires a highly disciplined, multi-phase technical roadmap that prioritizes systemic stability and careful operational overhead management. Architectural teams must begin by conducting an exhaustive data classification audit, pinpointing the specific high-risk information assets that require the ultimate protection of homomorphic execution pipelines. It is mathematically unfeasible to encrypt your entire global data ecosystem immediately due to the intense computational expansion factors inherently associated with modern homomorphic encryption mathematics. Therefore, organizations should initially pilot their FHE processing pipelines on low-parameter internal models before attempting to migrate massive, multimodal production clusters to encrypted execution frameworks. These initial small language model pilots allow your infrastructure teams to establish accurate baselines for processing latency, token throughput degradation, and network bandwidth expansion variables. During this testing phase, engineers should focus on optimizing the parameter selection rules within the encryption software, balancing security levels against the required inferencing execution speeds. Once these low-parameter pilots achieve stable benchmarks, the architecture can be systematically expanded to utilize specialized hardware accelerators like application-specific integrated circuits and advanced graphics processors. Hardware acceleration is absolutely vital for reducing the mathematical processing overhead of FHE, making real-time encrypted artificial intelligence inference accessible for large-scale enterprise production environments. Simultaneously, organizations must integrate their homomorphic pipelines with existing identity federation and access management systems, ensuring seamless validation across hybrid cloud deployments without exposing any keys. Continuous monitoring protocols must be deployed to track the operational integrity of the distributed cloud servers, verifying that no unauthorized code modifications occur within the hosting environment. As the deployment scales, governance boards must conduct regular risk assessments, aligning their cryptographic configurations with evolving global security benchmarks and post-quantum threat matrices. This iterative scaling methodology minimizes operational disruptions while building a deeply resilient enterprise architecture that inherently protects sensitive corporate capital against unforeseen vector threats. The definitive future of cloud-hosted artificial intelligence processing depends entirely on our collective ability to guarantee absolute information privacy without degrading computational throughput or operational velocity. By establishing advanced compute encryption as your baseline standard, you effectively insulate your corporate networks from external volatility while positioning your teams at the absolute forefront of technology. Embracing this sophisticated cryptographic framework ensures that your organization can confidently navigate the complex digital landscape, unlocking ultimate cloud data privacy through the power of pure mathematical architecture. Stop guessing your tech strategy and wasting your time. Subscribe to Enterprise Tech Brief right now. We deliver zero-hype, pure architecture. Master enterprise AI, cloud transformation, and cybersecurity completely free to future-proof your career and accelerate your technical domain knowledge. Hit the subscribe button.